Welcome to the fourth and final part of Lecture 1 on this course on chemical process design. In this final part of Lecture 1, we're going to look briefly at another set of documents that chemical engineers use during the design process, datasheets. Datasheets accompany the P&ID and give information that other engineering disciplines can use to further the mechanical design, control design, or instrumentation design. They can also be used to assist procurement. Datasheets usually appear as standard items, containing lists of information that require completion, not all of which will apply, and sometimes space is given to provide a drawing of the unit operation that the sheet concerns. We will also examine a relative of the datasheet, the interlock schedule, which is used to assist the control design of batch processes. So let's start by thinking about process datasheets. Process datasheets effectively give the basic process parameters for the design of specific individual items of equipment. And you'll find individual datasheets pertaining to things like pumps, to pressure vessels, to heat exchangers, to fired heaters and furnaces, since they're significantly different from shell and tube heat exchangers, to compressors, and so on and so forth. For items such as distillation columns, you'll find you might need to use more than one datasheet. You'll have a datasheet concerning the pressure vessel, which is the external casing, if you like, of the column, and then a separate datasheet for the internals. So you can then specify your packing or the number of trays and so on and so forth. Now, when you look at a datasheet, you'll find that there are lists of information. And these proformas are there as a prompt to remind you of the sort of data that's required for the other engineering disciplines to sit down and do their job. If you like, you consider datasheets to be the main means of communication between the chemical engineer and the other engineering disciplines. So, for example, with a pressure vessel datasheet, you can sit down with a mechanical engineer and discuss with them what it is that you want them to design. So, all these datasheets give other engineers all the information they need, and it's important that that information is complete and present, hence the reason why you have these prompts. If we think about the mechanical design a second, it's not the job of the process engineer to do the mechanical design, but he or she must have sufficient knowledge of the principles of mechanical design in order to be able to produce a drawing that gives all the information that the mechanical engineer needs, and we'll have a look at an example of such a drawing in a minute. So the other information you'll need is things like the temperature range, the pressure range, what other components go together to assist the design to work. You're not usually, although you can, specifying the type of material or the thickness of material and so on and so forth. But the mechanical engineer, when looking at the temperature range, the pressure range, and the required corrosion allowances, can also make those decisions for themselves. So let's have a look at a sample pump datasheet, and you'll see that that pro forma format is very much in evident, and we'll see that the first section gives general information about the location and type of pump. The second section gives all the quantitative data for the fluid, for the pump operation, and it gives the normal quantities, for example the normal flow rate or the normal vapour pressure or the normal dynamic head, the maximum and the minimum values, which are all very important to know when it comes to specifying what pump to buy. The next section gives safety information, along with some other information such as, for example, materials, a type of driver, a motor or otherwise, and the type of seals that the pump has on it. The final piece is right at the bottom, sometimes easily overlooked, and this demonstrates the principle that calculations are always done more than once. And so here you have a box for the engineer to sign who's done the calculation and checked it, and then another box for somebody else to sit down and sign who's gone and checked and approved the design. So don't forget, a design is never done once, it's done multiple times such that it can be ensured to be correct. Let's have a look at a vessel datasheet. You'll see on the right hand side again you've got your pro forma information, and you've got information here pertaining to pressures and pressure ranges, temperatures and temperature ranges, and the likely physical properties of the material in there, for example the liquid density and so on and so forth. If we change our attention to the drawing, you'll see that there is actually quite a level of detail shown here, and this is the level of detail that I would expect the chemical engineer to produce. We've sat down and we've thought about how this vessel connects to the outside world. we can see that there are a number of flanges illustrated on here connecting to the process, but also flanges that connect to instrumentation, connect to vents, connect to drains, connect to nitrogen supplies. There's a great big flange in the middle that allows people to get in. And note that all of these flanges have got dimensions associated with them, that the pressure vessel itself has been dimensioned, and that the location of these flanges has been specified on the pressure vessel. Note that the vessel is supported. We've got 2 support saddles, and that we've worked out the width of those support saddles, so we know roughly what the bending moment of that vessel is and how far apart those supports need to be to prevent excess deformation. So do pay close attention to the elements of mechanical design that you are able to carry out, because that will then give a very accurate set of information for the mechanical engineer to then go and complete the design. Let's have a look at the interlock schedule. As we said in the introduction, the interlock schedule is that piece of information that allows control engineers to go and specify how a batch process works. So let's look at a unit operation. So here on the whiteboard I've got a stirred tank reactor that is aerated. We have it operating in batch mode. So this reactor goes through a sequence of operations in order to complete its duty. First of all, you've got to fill it. When you fill it, you open the 2 valves at the top, 1120 and 1121, to allow material in. In operation, we put air sparge in, and so valve 1122 is open and 1120 and 1121 are shut. Note that we should really also illustrate a vent on here to allow gases out when we're filling, when we're emptying, and also the unreacted gases from the air sparge. Valve 1123 is only open when we drain the reactor down, and the motor M1130 actually only goes and stirs the paddles at a certain time. And so we need to be able to communicate our design intent to the control engineers. And here's one way in which we can do that. If we put all the essential items of equipment in a grid type matrix, so we've got our 4 valves and our motor, both on the horizontal and the vertical sides of this matrix, we can then say when the state of a valve changes with the change of state of another valve. So for example, let's take the column which is entitled valve 1120. We'll see that when valve 1120 is open, we have valve 1121 open. So those are both our feeds going in at the same time, but all the other valves are closed and the motor is stopped. Valve 1121, when that's open, well, its counterpart 1120 is open, and again all the other valves are closed and the motor's stopped. When valve 1122 is open, that's our air sparge going in, we're no longer adding liquid to the tank, so 1120 and 121 are both closed. We're not draining the tank either, so valve 1123 is closed, but our motor is going and our tank is being stirred to allow, hopefully, enough effective mass transfer between gas and liquid phases. If we look at valve 1123, we'll see that that's open only when everything else is closed. The motor's stopped, we're just draining the tank down. And if we look at M1130, we can see that it's stopped when valve 1120, 121 and 123 are open, and is running when 122 is open. And so there's a little bit of duplication of information here, but it does provide a cross-check to allow us to see that the operation is indeed correct. So that's one way in which you can communicate control information of batch processes. So let's recap a few key points. Data sheets are really important. They accompany the P&ID and give additional information that is very, very important to the mechanical design, control design, instrumentation design and procurement of items of equipment. They are used by all engineering disciplines during the design process. And the interlock schedule in particular is a vital piece of documentation that allows the chemical engineer to explain the control sequence of a batch-based process.